Today's topic is going to be acids and bases. This is going to be our like little bit of dipping our toes into chemical reactions. After we finish filling out the periodic table, we're going to go pretty hard into types of chemical reactions. But today's going to be a chance to just talk a little bit about one of the sort of categories of chemical reactions that can happen. So today we're going to talk about acids and bases. Our goals for today, we want to learn the properties of acids and the properties of bases. We want to make sure, we want to remind ourselves how to read a chemical equation. So not just a chemical formula for a single molecule, but an equation for a reaction that's happening when multiple chemicals are reacting with one another. And then we want to be able to predict when an acid and a base react with one another, what the product of that reaction will be. So we're actually going to start talking about chemical reactions today. So when we ask what the hell are acids and what the hell are bases, the thing you need to understand about these is that these are categories of chemicals. In the same way that salt is a category of chemical, acid is a category of chemical, base is a category of chemical. And one of the types of questions that are going to be on your chemistry final are things like, hey, given this formula, do you think this is an acid? Do you think this is a base? Do you think this is a salt? Right? So that's one of the types of questions you will see on the chemistry exam when it eventually happens way down the line. There are many, many, many different acids that exist, and there are many, many, many different bases that exist. But broadly speaking, they're all going to have certain things in common. So all acids are going to have certain things in common, and all bases are going to have certain things in common. So let's take a moment and talk about these properties. Acids. You encounter acid. You're probably used to thinking about acid as like a big, scary chemistry word, and you're like, ooh, acids, like I fall into a vat of acid and eat my body, and horrible things will happen.
But there's acids in oranges.
Yeah, there's acids in oranges, there's acids in grapefruits and lemons, and all of the all the citrus plants have acids in them. Most fruits have some measure of acidity to them. Acids, you actually have a built-in chemical sensor on your tongue that is capable of detecting the presence of acids, right? Both your nose and your tongue are very complicated, very capable chemical sensors, and they can detect the presence of acids, and they can detect the presence of bases. Acids, your tongue will detect, and your brain will interpret that detection as tasting sour. So you can think in your head of many things that are sour. All those things are probably slightly acidic, right? So lemons, oranges, any kind of citric fruit, vinegar, lots of sour candies. Have y'all ever seen that like white dust that's always on sour candies? Yep. That white dust is just powdered citric acid, right? So acids will taste sour. Bases will tend to taste bitter. They have a very different flavor. In terms of how they feel, like if you are touching an acid or if you are touching a base, acids just feel like water. There's no special feel to them. But bases have this kind of weird, soapy, almost slippery feeling to them. And if you would like to test this out for yourself, on the tray in front of you, there is a little bottle. One of them is labeled vinegar. One of them is labeled baking soda, although some of the labels on the baking soda are a bit worn. If you want to, you may take one drop of that and put it on a finger and rub it between your fingers just to feel like physically what that sensation is like.
Of which one?
You don't have to, the baking soda, which is a base. And you'll notice it has just like a kind of slippy feeling to it, yeah. Right? It feels slippery. That is a thing that tends to be common of bases in general. This is a very weak base. It's not a strong base like the ones we learned about yesterday that are made of an alkali metal and a hydroxide anion. Baking soda is not particularly strong. This is just a little bit of baking soda mixed with water. But it is enough to make you be able to feel that like slippy feeling, right? That is really characteristic of bases. Acids and bases can react with one another. When an acid and a base do a chemical reaction, the things that react in a chemical reaction we call reactants. So reactants react, and they can react with one another. And what they produce after the reaction, we basically take these elements that make up an acid, the elements that make up a base, and we can sort of recombine them into new chemicals. The new chemicals that are produced in an acid-base reaction, they'll always produce water as one of those chemicals alongside some form of salt. And exactly what salt you get is going to depend on what your acid was and what your base was. But broadly speaking, acid-base reactions follow a really simple pattern where the acid and the base come together, they react with one another, and then you end up with two new things made out of the pieces of the acid and the pieces of the base. And those two new things are always water and salt. So they can actually react with one another.
What does caustic mean?
Caustic is a word that refers to things that can cause like chemical burns. So acids can corrode metals. If you want to do a little bit of an experiment at home, I actually have at the end of this lesson like a number of recommendations for home experiments you can do, which are a lot of fun. One of the most common ones is to take a can of like Coca-Cola or Pepsi or a similar soda, because sodas contain an acid called carbonic acid, and that acid over time can eat through a nail, right? It can corrode iron. And so what you can do is you can take like a nail, stick it in a glass of Coca-Cola, let it sit for a while, and you can see the nail dissolve,
Where
right?
are you going to get the nail?
I mean, you'd have to go buy a nail. You probably have a nail in your, like...
Oh, I thought you meant like a finger.
Oh, no, not a fingernail, not a fingernail, no. like a nail made of iron.
Sorry.
People think of acids as being like this dangerous thing. Really the one that you have to worry about more is bases. Now, the baking soda we've got here that I let you touch is very mild and is safe to touch. But a lot of strong bases are actually quite dangerous for people. Bases react with like fats in human skins and can literally rend fat into soap. One of the ways in which soap is made is people take really strong bases and they mix it with like lard or some sort of fat, and that is like where we get our soap from. And when you think about how much fat is in our skin and the fact that that can react with bases, it's actually quite dangerous to get strong bases on your hands, right? So like later on this year, when you get to see our sodium and water reaction, one of the byproducts of that reaction is sodium hydroxide, which is a strong base. And we're gonna have to be really careful not to touch that water, because if it's a strong base, then it could literally give you chemical burns, right? So caustic means it can give you chemical burns. What those look like is like little red spots that feel like itchy and burning almost. It's an unpleasant feeling if you get a strong base on your skin. So even though people tend to like have heard more of acids, it's really bases that are more dangerous for people. Yes, Yossi?
So I'm assuming this is litmus paper?
That is litmus paper, yes.
What is it?
So litmus paper is an example of something called an indicator.
Oh.
Indicators is another class of chemical, and the deal with indicators is that they basically can react in a way that sort of makes a chemical reaction obvious. Indicators change color in the presence of an acid or a base. One of the most common indicators is this stuff called litmus paper. It's made out of a plant. Lots of plants actually create indicators on their own. A lot of plants that are like bluish or purple in color, like red cabbage or blueberries, have an indicator in them that can actually tell whether there's an acid or a base nearby. And so this paper is made out of a plant that has this indicator in it. And what litmus paper does is it changes colors in the presence of an acid or a base. So on your trays at your table, you have a weak acid and a weak base. So neither of these is strong enough to like be dangerous. It's just vinegar and baking soda, right? And you have two little petri dishes and two pieces of litmus paper. What I want you to do is just make sure everyone at your table can see it. But put a drop of the vinegar on one of these pieces of litmus paper. Try not to make a mess, because we're going to have to clean up after this. And put a drop of the baking soda water on the other one, so you can see what happens to the litmus paper.
Which is which?
The two bottles should be labeled. So one of them should be clearly labeled vinegar, one of them should clearly be labeled. Yeah, so basically a drop of the vinegar on one of the papers and a drop of the base on the other paper. So many of you are saying, hey, ours turned green instead of blue. Why is that? The answer there is a scale, and this litmus paper is actually designed for you to be able to tell like roughly how basic is something. So if something is neutral, it's in this sort of orangey zone, orangey to yellow zone. Things go to like a dark orange if they are a little bit acidic, and to kind of a pinkish color if they're really acidic, and they go to a green if they're a little bit basic, and a blue if they're very basic. So because this baking soda is a weak base, most of you will have it be turning more of a green color than a blue color. But some of you might end up with like a little bit, these are not precisely mixed, so if I got you a little bit more basic solution, you might end up with a blue one rather than a green one. So this is stuff called litmus paper, and it changes color. Oh yes, if you want to, you can do a little bit of experimenting with this. There's some folks who put like one drop on one end of the paper and a different drop on the other end, and can see the gradient in color between them, where it's got that neutral color in the middle, right, as folks do this. So we can see the neutral yellow going to the basic blue or green, and the acidic red or pink.
These are so pretty.
Acids and bases are particularly fun because this, like, indicators really are the origin of, like, if you've ever had this concept of chemistry and this picture in your head of chemistry being done where you see like a beaker and it's got a liquid and the liquid is one color, and then you do a chemical reaction and then the liquid changes colors, those are indicators, right? That's why that stereotype of chemistry as like a beaker that changes colors, right? That's where it comes from. It comes from indicators. And if you enjoy this, let me tell you, you can make your own indicator at home. The best thing to do this with is purple cabbage or red cabbage. If you take some purple cabbage, you cut it up, or even better, put it in a blender, and then like boil it in some water for a little while, you'll end up with this like, that cabbage water is actually an incredible indicator. And it turns this beautiful, beautiful colors, like it turns this like reddish, pinkish color in an acid, and this bluish color in the presence of a base, just like litmus paper does. And so you can use that to see whether like things at your house are acids or bases. So if anyone wants to have like a fun thing to do this weekend, go grocery shopping, grab yourself a purple cabbage, cut it up, boil it, and then just like have a little glass of it and try adding different things from your household to it.
What
right?
do you mean,
like squeeze a lemon onto it, see what happens, right? Grab a fresh little sample and throw in some baking soda, see what happens.
Is that like why butterfly P2, whatever that is? Like I feel like, isn't it, it's purple and then it turns blue? Or it's red and it turns blue?
That does sound like it could be an anthocyanin, which is a type of indicator.
Yeah, butterfly P2.
But this is a very fun way to explore acids and bases at home, and I highly encourage y'all to try playing around with acids and bases at home. Other things to note about acids. Acids, in addition to eating through metals, can eat through things like calcium carbonate, which is in lots of creatures' shells, right? So think like the shells of corals, right? Or like mussels or clams or things. Acids will actually eat through that. So if you want to see one of the consequences of like ocean acidification up close, a thing you can do is you can take a glass of vinegar and just stick a raw egg in there. Leave it in there for a while. You can see the vinegar will gradually eat away. You might have to change the vinegar once or twice, but it'll literally eat away at the shell of the egg, leaving just the like membrane inside the egg, still holding it, still egg shaped, but you can eat away that shell.
Wait, but will it
I wouldn't recommend it.
How do you know when to take it out, or will it not eat away at the membrane as well?
And when it stops eating away at the shell, then like change out the vinegar. If you do that for a couple days in a row, just like have an egg in a glass of vinegar and like change it daily for a couple days, you'll be able to see that the shell of the egg is eaten through, right? It'll do that. And then you've got like a cool membrane that you can play with, and you can do all sorts of fun experiments with osmosis, which is a big idea in biology. So there's a lot of fun things you can do with acids, just with like household materials that I encourage you to play around with. And there's a section on the website with some like at-home experiments you can do. So those are all options for things you can do to play around with this. Chemically speaking, many acids are going to have hydrogen as their cation. This is not true of all acids, but it is true of many of them. So you'll oftentimes have H+, a hydrogen cation, present in acids. If you have H+ as your cation and a halogen as your anion, that's going to be a strong acid. Bases tend to have OH- as the anion. And remember, if you have an alkali metal as your cation and OH- as your anion, that's going to be a strong base. And again, I said this yesterday, I said this the day before, but it bears repeating. Acids and bases are all about water. If we imagine water as an ionic compound, what we think about is a hydrogen cation and a hydroxide anion. If all you have is plain water, then you have the same amount of hydrogens as you have hydroxides. So if what you have is pure water, right? Nothing but water, it would be totally neutral. It would neither be an acid nor a base. There's a scale we use to talk about how acidic and how basic things are. It goes from 1 to 14. And on that scale, low numbers are acids, so like a pH of 1 is very acidic. High numbers are bases, so like a pH of 14 is very basic. And 7 is neutral, right? So like pure water should be around 7, right? So acids are things that tilt this in favor of the hydrogen cation. Bases are things that tilt this in front of the hydroxide, in favor of the hydroxide ion. That's why if you have an alkali metal and a hydroxide ion together, it's a strong base because it has these hydroxide anions. That's why if you have a hydrogen cation and a halogen, it's a strong acid because it tilts things in favor of the hydrogen cations. Right? So acids and bases are really fundamentally about water. So if you've got a cup of water, right, most of it would be together as H2O, but sometimes these ions separate out, and you'd have, some H pluses and some OH minuses just floating around. But if we add in a chemical that creates more H pluses, that's an acid. If we add in a chemical that causes there to be more OH minuses, that's a base. So it's about hydrogen cations and hydroxide anions. Extra hydrogen cations make something an acid. Extra hydroxide anions makes something a base. Here we have a chemical reaction. So this first one is just to show you how we read an equation. Equations in chemistry are a lot like equations in math, except they only go a particular direction. Right? So here we have reactants, which are the things that react. And we have products, which are the things that are produced. So looking at this equation, what it's saying is, hey, 2 molecules of hydrogen gas, H2, and a single molecule of oxygen gas, O2, could come together, that's what this arrow means, to create 2 molecules of water. So you can see here, in total, we have 4 hydrogen atoms, because there's 2 molecules of H2, so that's 4 hydrogens in total, and 2 oxygen atoms, and together we can rearrange those to make 2 molecules of water, because 2 molecules of water has 4 hydrogens and 2 oxygens. So equations are supposed to be what we call balanced, which means that we start with the same number of atoms as we end up with. Because in a chemical reaction, what we're really doing is we're just taking these atoms and we're rearranging them. Yes, yes?
Are indicators expensive?
Not terrible. Well, it depends on the indicator. Litmus paper is quite cheap, so this is not terribly expensive. Honestly, they're not very expensive. You can also get bromothymol blue. So bromothymol blue is an indicator that if something is neutral or basic, it's blue, and if something is acidic, it turns yellow. There's also phenolphthalein. Phenolphthalein is clear if something is acidic or neutral, but it turns magenta if something is basic. So these are all things that you could use to tell how acidic or basic something is. So here's some more examples of chemical reactions. You can see we have the reactant side. On the reactant side here, we've got methane gas and oxygen gas. And then on the product side, we're producing carbon dioxide and water. And you can tell looking at this, hey, we came into this with 1 carbon, we come out of it with 1 carbon. We came into this with 4 hydrogens, we come out of it with 1, 2, 3, 4 hydrogens. We came into this with 1, 2, 3, 4 oxygens, we come out of it with 1, 2, 3, 4 oxygens. So the key idea behind chemical reactions is we're not creating any matter, we're not destroying any matter, we're just rearranging it. Remember the Lavoisiers, Marianne Lavoisier and her husband, right? They came up with this law of conservation of mass, and chemistry follows that law exactly. Yes, yes?
Is that carbonated water?
So carbon dioxide is in carbonated water, but here that would just be like carbon dioxide, which is a gas, and water, which is a liquid.
Oh.
So the gas would probably bubble up.
But if you had more water?
You could create carbonated water pretty easily. So here's another example. Here we've got 2 waters breaking down into hydrogen gas and oxygen gas. And again, just the key idea here is I want to show you that all chemical reactions is just rearranging these different atoms into new molecules. So we still have the same number of atoms as we started with, we've just rearranged their form. Okay, so that's what a chemical reaction really is. Now, acid-base reactions are a very specific kind of this. When an acid and a base react with one another, you always start with the acid and the base. And we always get the same, well, we always get 2 products, one of which will be water. The other one is going to be some kind of salt, some kind of ionic compound. So an acid and a base can come together to create water and salt. So for example, hydrochloric acid, we can tell this is a strong acid because it's got a hydrogen cation and a halogen, chlorine as its anion. That can come together with sodium hydroxide, which is a strong base. We can tell it's a strong base because it has an alkali metal as my cation and a hydroxide anion as my anion. Those 2 things can come together and basically the cations swap positions. So this hydrogen, instead of being with the chlorine, comes and hangs out with the hydroxide. I have hydrogen hydroxide. That's water. That's just H2O. Whoa. This is just water. And the sodium that was with the hydroxide switches places with the hydrogen.
So
we have sodium chloride. That's table salt. Yes, Yossi?
So it's salt water? Or just dissolved?
Well, it's salt and water. 2 separate products.
Okay.
Yeah. This is going to be on your class kit. You're going to have to fill in. Like, I'll give you the reactants, and then you're going to have to say, like, oh, what are the products of this going to be? One of them is always going to be water. The other one is going to be some kind of salt. Here's another example. Again, a strong acid and a strong base. We can tell that this HF, hydrofluoric acid, is a strong acid because we've got a hydrogen as my cation and a fluoride, which is a halogen, as my anion. And remember, a hydrogen cation plus a halogen is a strong acid. And then for the base here, I've got lithium hydroxide. That's a strong base. I can tell it's a strong base because lithium is an alkali metal, and that's bonded with a hydroxide anion. And again, an alkali metal with a hydroxide anion gives us a strong base. And together, those come together, we create water and lithium fluoride. What type of chemical is lithium fluoride? Salt. It's salt, right? Acids plus bases gives us water plus salt. Right? That's how these chemical reactions go. Right, here's another example, hydrobromic acid plus potassium hydroxide. Again, our cations are just swapping places. So we end up with water and potassium bromide is our salt. So all of these, all right, now I want y'all to predict the answer. If we take hydroiodic acid and rubidium hydroxide, a strong acid and a strong base, go ahead and write a moment in your notes. What do you think the products of this chemical reaction are going to be? There's a very clear pattern here. Right? Write it down in your notes. I'll give us a moment before we have somebody answer. All right, Shep, what do you think we're going to get?
HOH plus RBL.
That's an I, but yes, HOH plus RBI. So rubidium iodide would be our salt, and water, of course, is the water here. Now, if y'all want to experiment from home, here are some fun things you can do. Stick a raw egg in vinegar for a few days. Right, you can see the vinegar eat through the shell of the egg. You can make an indicator with purple cabbage and then use that to test out a whole bunch of different substances and see what changes color. So if you enjoy playing with the litmus paper, this is actually super fun and I highly recommend it. You can try sticking an iron nail or something metal in a glass of Coca-Cola for a few days to see what happens there, because acids tend to degrade metal. So those are all options for things you can do. You do have a class kick today. Before you can do the class kick, I do need you to do the following things. You need to take your litmus papers, throw them in the trash. Make sure that I need you to rinse and then dry your Petri dishes. And then come back to me and I will give you fresh litmus paper to go in those trays for the next group. Once your table has done that, you are good to start today's class kick. All right, enjoy, folks.